I'd now like to talk about the Claisen reaction. In the aldol reaction, we were using an aldehyde and ketone as the reactants. Now with the Claisen reaction, we're using esters as the reactants. When we do a Claisen reaction, what we're doing is having two equivalents of the same ester, and we end up with a beta-keto ester as a product. All right, let me show you the mechanism for this. In the first step, we're going to have the alpha hydrogen removed off one of the ester molecules. And that's going to be removed by the OET negative, that's from up here. And we end up with this anion, which is stabilized by resonance because it's next to the C double bond O. Right, let me point out here that the base, the OET minus, and this OET, and of course the solvent for the base, all must match, because if that doesn't happen, then what happens is we get some transesterification processes possible, which will end up changing the product or causing product mixtures more likely. So if we were to use OMe minus, for example, what could happen is that the OMe minus could come in and replace the OET in a standard transesterification type process. Most likely though, it wouldn't replace all of it. You'd end up maybe with half of it with OMe and the other half with OET, so we'd end up with two products here, one with OET and one with OMe, and we always want to try and avoid extra products if we possibly can. So that's why we've got to make sure that everything in the base matches what's on the ester. Alright, continuing on with the mechanism, we can now have this come in and attack the other equivalent of ester. And at this point, it's pretty much reacting the same way as the aldol was. Now this is where things get a bit different than what happened with the aldol. Now because we reacted an ester, the negative from the O comes down and kicks out the OET. And we end up getting what looks like our product. But the reaction does not stop there. Here's the issue we're facing. We have a basic solution. We haven't added the H plus yet into the reaction mixture. We've got a basic solution and we have acidic protons present in our compound. So what's going to happen is the OET minus is going to take the hydrogen off the carbon that lies in between the two C double bond O's. Remember that such hydrogens are very acidic because the resultant negative charge can be stabilized by two C double bond O groups. Alright, so that puts a negative charge here, and remember that that negative charge is very stable. So as soon as this forms, OET minus will come along and we will get that proton removed. The purpose of the H plus in the second step is so that we can add that to the negative charge and we end up with our product. Now I want to point out that all the reactions all the way down to here are reversible, but once we get the negative charge formed here at this point, once we get that negative charge formed, the reaction is not reversible up through this way. So the only thing it can form is this negatively charged species, and it sort of pulls the reaction through the product. So then the negative will react with the H plus, which we will get in the second step, which we add in the second step, and that gives us that product. All right, just let me make a comment about a comparison between the aldol and Claisen condensations. Now, in the aldol condensation, we get pretty much the same thing happening, but here you've got an O negative, and because there's no leaving group here anywhere, the O negative can't come in and kick anything out. That's what happened in the Claisen reaction. The O negative came down and kicked out an OET. That's because we actually had that there available as leaving group. Aldehydes and ketones don't have that option. That's why we get a different kind of product when we do the aldol than when we do the Claisen reaction.